Good afternoon. I'm Tak. I'm a server-side engineer and currently leading OpenChat development team. I will present Inside OpenChat session today. So, welcome to my talk. よろしくお願いいたします. So, in this session, I will talk about the internals of OpenChat, especially about how we designed a new messaging service with scalability from the starting point. So here's the agenda. So I will start the short introduction to OpenChat and give you some background and its initial requirements. And then I will explain 3 technical points about scaling the service, and finally summarizing what I said and show you some future works. Then let's get started. So have anyone used OpenChat here? Please raise your hand if you have. Oh, more than I thought. Thank you. You can put your hands down. OpenChat is a new messaging service launched in Japan August this year. So it's also open in Indonesia and Thailand in 2017 and 2018. It enables Line users to communicate with people having the same interests. So you don't have to use your own Line profile. You can set a different profile in each OpenChat. So here are the entrances. You can touch OpenChat from Home tab or touch Create an OpenChat button from Chat tab. If you click OpenChat, you will reach this page, so-called OpenChat Main. In Main, you can discover other OpenChats. There are sections like popular keywords or like trending OpenChats, recommended sections. So also, you can search OpenChat through search keywords. This page might not be the same as what you can see now. Each country's local team manages the contents and also controls the sections. After finding the OpenChat you like, then you select the OpenChat and you will reach OpenChat's home. In OpenChat Zone, you will see its name, profile image, description, and member count, and more information. Then if you want to try it, then click the Join button and enter a new profile information like your name or profile image. After click done, now you are in that OpenChat, so you can start talking with other people. The usage is almost same as Line. You can use your own stickers too. One interesting thing about it is that you can see the chat history by scrolling up. So it's possible to see what people have talked about previously. In Chat tab, OpenChat's chat rooms are listed with a small green OpenChat icon, so you can identify them easily. It was the short introduction to OpenChat. You'd roughly figure out what this service is about. So let's get into the details. I will explain the background and its initial requirements. So OpenChat was started from one mission, closing the distance, just like Line. So here's a simple diagram about OpenChat's target users. The x-axis is about the relationship. So as you go to the left side, it's closer relationship like family or friends. If you go to the right side, it becomes distant. So you may or may not meet these people in this relationship in person. The y-axis is about the size of people, so bottom is small, going up gets larger. If I put a line here, it's currently located in the left bottom position, since it's for close relationship and also small size group. So OpenChat is trying to expand Line's user base, including distance relationship and also bigger size of communities. So it targets various size of communities and also various kinds of relationships. So currently, the service is targeting the middle and the right side in this matrix. So based on the strategy, its requirements were in 3 categories. First, increase a group size about 10 times bigger than the current chat members by allowing multiple chats in one single open chat, about 2,000 times bigger than the current group size. Second, support community features like member management or admin co-admin features. So third, enhance chat features like showing chat history or deleting messages by admins. Based on these requirements, we designed and implemented OpenChat service. There are other interesting topics about OpenChat, but in this presentation, I will focus on the scalability part of OpenChat, including its technical challenges and also the solutions we try to make. So the main challenge starts from the first requirement, increase the member size. Logically, it's like this. By increasing member size, more people could come to a chat or a group. More people means more actions. So in a chat, people send messages, update their market reads, also join, leave at any time. We call these actions as events. So more people would generate more events in a chat. So those increased events may cause two problems. The first is the event delivery part. All those generated events need to be delivered to users exactly to their client devices. More deliveries mean the increased size of payload and also increased time to deliver. The other problem is about the hotspots. It's highly probable to have very active chats in a service like this. So you can imagine like sportscasting of very important event like Olympics or the fan club meetups about a famous celebrity. Lots of people are just online and interact and talk to just one single chat, and that makes hotspots of the stories and give overhead to them. So in extreme case, those hotspots can make the service down if the server is not properly designed. So from these technical challenges, here I divided the problem into three categories. First, the size of members. Second, the delivery of events. Third, the stability of servers. So I rephrase them like this. The first mission is scaling storage by effectively storing members and also accessing those members. So the system must be okay even though the member size increases. The second is about making effective delivery when passing events to clients. So delivery should be fine even though the number of events increases. The third is letting servers endurable by effectively preventing application servers from failures. Does that make sense? Then let's discuss each topics one by one. The first topic is about storage. Scalable storage starts with choosing the right solution based on the usage. So for that, the team investigated various usage patterns of OpenChat. The requirement is storing lots of users and accessing those users. So in OpenChat's use case, 90% or more accesses from application servers to storages are reading list of members. So this is related to the second requirement, delivery. So for example, a sent message needs to be delivered to all the members in a chat. So to do that job, server needs to know all the members, which result in listing. Also, listing members is not just one pattern. In OpenChat, members have attributes like roles, admin, co-admin, and also membership state, joined, left, kicked out. So it is necessary to list members with multiple criteria and also sort them by multiple options. So from the perspective of storage, it means that secondary indexing is required. So based on the requirements, our choice was MySQL. Relational databases fits well with secondary indexing, and also among many relational database solutions, MySQL was officially supported in line. So we considered other SQL or NoSQL options, but it was neither supporting secondary indexing well, nor being supported by line well. So after choosing MySQL, then we needed to think about how to scale MySQL with sharding. So the team also investigated the various sharding solutions. So among many sharding strategies, pre-sharding is the one OpenChat uses. Pre means sharding from the starting point with the fixed number. This fixed number does not change in the life of the service. There are two reasons why we chose pre-sharding. First, it's easy to replicate data in MySQL for expanding or shrinking from the perspective of DBA. It's also, most of the tools it already work with MySQL inline also works with this pre-sharding solution. So DBA's operation does not change that much with pre-sharding solution, so that's why we chose pre-sharding. Here is the way we implemented pre-sharding. So number of shards should be reasonably big for scalability, so we chose 12 bits for shard ID. Since OpenChat uses 64-bit integer for IDs, the rest bits are used for local IDs in a single shard. So 12 bits means that it can have 4096 shards, and they are called logical shards. But we actually don't need 4096 hosts when the traffic is low. So the logical shards are grouped together and located in certain number of physical hosts. This mapping information between logical shard and physical host is used by application servers. So application server knows which physical host and which logical shard it needs to access when an ID is given. But if the traffic gets larger and one physical host is not possible to handle those traffic, the expansion is necessary. In that case, the expansion works like this. In this example, one physical host is expanded into two hosts. So DBA first prepares two new DB hosts and start replicating from the original one. Then, if the replication is done, we update the mapping information and make the application servers use the new host. After that, after checking, all the read-write accesses are migrated to the new host, and the original host is not used anymore. DBA is ready to clean up the original one. So the idea is straightforward, but there was no good library to support this when we designed and implemented OpenChat. So OpenChat team had to implement our own pre-sharding library. What we implemented have three parts. The first part is a shared data model for the mapping information. And second is the client library named data source, which makes DB connections and also handles logics when that mapping information is updated. The third is the manager, which provides the API to change those mapping information and also stores them in the backend storage. We are using Apache Zookeeper for that. With this implementation, we did several operations like DB upgrade, failovers, and so on. And the big one we conducted in 2018 was the twice times expansion. Actually, the expansion is a little bit more complicated than what I explained before, because we have master-slave setups, and also we need several steps to follow in order to lower the number of failures during this job. And we thoroughly rehearsed in our testing environment and did the same thing in the production environment. Everything worked pretty well, and we did not have any failures at that time. So let's move on to the second topic. It's about delivery. So it's mostly about client-server communication and related data models. Before talking about the delivery, let me briefly explain about event again. So an event is a result of a user's CUD action, meaning create, update, and delete. The CUD action is directly related to the data models OpenChat uses. So here's an action like sending a message, creates a message data model in the storage. And the creation of a message data model creates two events. So to the sender, it's a send message event. To the receiver, it's a receive message event. Other actions like joining, leaving, mark as read does the same thing. Now you can see the problem. Many events by many people in a chat. But OpenChat server needs to deliver all those events to the user's device anyways. So we cannot limit users' behaviors. So we had to answer the question, how can we deliver all those events effectively? If you see the problem a little bit, three logical ideas would come up. The first is delivering events when necessary. If we think from a user's perspective, what the user needs is not retrieving all those events sequentially, but is seeing those events in an appropriate time. Like when a user is looking at a chat and it needs to download those events in a chat, but the user is looking at another chat, then it's not necessary to download the messages from the other chat. So that's the basic idea, and that's what delivery events when needed means. The second idea is about about an obvious one. It's if the total number of events is reduced, then event delivery would take less time and also consume less traffic, so it is possible to scale more. If the first and the second idea are implemented, adjusting the delivery frequency would help effective delivery. I will explain how we implemented these ideas one by one. So let's say that these are all the events a client device needs to download. Here are 4 types of events: blue, red, green, and yellow. Let me explain the meaning of these colors later. So would you imagine that what the top frequent events in OpenChat? It's a messaging service, so those are messages and mark as reads which are occurring in chats. So their portions are more than 95% of all the events. So those events also can be downloaded to client only when looking at chats. So simply separating the events in chats from the other types of events can give us a lot of benefit. Based on this simple idea, so we categorized events into 2 types. One is chat event, all the events in a chat, including message, mark as read, join message, leave message, and so on. The other is user events, all the events outside of the chats. So for example, if you join a chat, and then that chat needs to show up in your chat list. And also, if an admin of an OpenChat updates its OpenChat's name, that update also needs to be applied in your chat list. So That kind of events are the user event, which the way to let client device know about these updates. By applying this idea, the long list of events you previously saw are split into 4 lists. So let's say the green ones are user events and the others are chat events. Then, so client can download each list separately. So when looking at the chat list, then it downloads the green ones, the user events. When looking at another chat, like blue one, then client downloads the chat events at that time. The next idea is making the number of events smaller. So let's imagine a situation like this. So there are 3 events at A point, and a new event comes. This new event is the update of the second event. Like, for example, like an admin updates a chat name and again changed it again. So then the previous event does not have to be fetched since the new one can overwrite it. So we call this event merge. A similar situation happens at B point. So if you see this diagram, there are 5 events in total, but at C point, it's okay to download only 3 events. So by merging events, the total number of events can be reduced quite much. So that's the basic idea we applied. So from the previous example, I said the green ones are the user events, and here it's labeled with some numbers. So here the same number means that the events from the same model. So, but after merging, the total 22 user events are reduced to 11, like 50% down. So in this example, I explained the user events, but chat events have the same mechanism. After applying those 2 previous ideas, more optimization is possible if server notifies when to retrieve events to clients. If many merges are happening, then slightly delaying the fetch can reduce quite an amount of events. For example, let's think about a chat with 1,000 online members and 10 people are sending a message in a second. So as soon as a message is delivered to a client, then that client will send mark as read right away. So then one message can generate 1,000 mark as reads. Then 10 messages means that 10,000 mark as reads. Then if 5 seconds is passed, then 50,000 mark as read would be generated. Without merging any of these, 50,000 mark as read needs to be delivered to clients. But if it is possible for server to wait for some seconds and let event merge happens, then only, like in extreme case, only 1,000 mark as read events can be sent and delivered to client devices. So in OpenChat, for this, there are 2 concepts, subscription and server push. Subscription is straightforward. By subscribing, client let server know, I'm interested in the events in this chat, so please notify me when there is a new event. Subscription can be made per user for user event and per chat for chat events. Server push is a method to notify client that there is a new event. So server push includes the information from which subscription this server push was made. So when notified, client identifies the subscription and tries to fetch new events from server. So here's the flow diagram. In this diagram, let's say this is for chat events. So there are 3 participants. line client on the left, OpenChat server on the right, and in the middle, there is an API gateway. Client calls an API named fetch event, and that request goes to the API gateway, and the gateway passes it to OpenChat server. Fetch events API includes the information like which chat the client wants to subscribe. Then OpenChat server gets that information and remember that this line client has subscribed to this chat. Then server responds directly, and the response goes back to line client. But after that, if a new message comes, a new event happens, then OpenChat server recognizes that it needs to notify to the client. Then it basically requests to the API gateway, sending a server push to the client, and after the server push is received by line client, it fetches the new event through the fetch events API. Currently, server push is implemented through speedy connection. It is between line client and the API gateway. Line is currently actively working on migrating to HTTP 2 now, so speedy-based server push would be replaced by HTTP 2-based server push soon. So after applying those three ideas, here's the final result. The first idea groups events into multiple lists. Then client can retrieve them whenever it needs. Then the number of events in list were decreased by event merging. And finally, by using subscription and server push, server can control the event delivery and optimize the delivery size. So let's see the reality in delivery part. This is usually happens when you use OpenChat, and this is how this idea is actually used. So when you see this chat list, many chats have like 999 plus batch counts. But when I open line client fetches all the user events and update the chat events, but it does not download all the messages. Then if I click a specific chat, and then it fetches the messages, and I can see those messages in the chat room. So that's how it works with these ideas. So let's move on to the final mission. The last mission is about making scalable servers, in this case, endurable server. So when OpenChat server was designed, around that time, what we observed frequently in line was thread busy problem when a component has an issue. For example, if a shard of Redis cluster has a problem, then all the threads in a server are blocked by it, and all the servers in which uses that Redis cluster are blocked by this, and the server cannot process the requests anymore. So this is a usual pattern when synchronous code is used in server side. In OpenChat's case, this could be worse because of the very active chats. Those super active chats can generate codes like hotspots of storages because it makes application servers read or write data from and to specific locations over and over. So it means that a shard or some shard can be down very easily. So our mission was finding a way of avoiding failures even though hotspots show up. As you can imagine, our solution is being asynchronous. The main problem is blocked threads by partial failures. So we thought that making our servers asynchronous would not block any threads, then the problem would be solved. So it really makes sense in theory, but being asynchronous was not that easy. So in reality, like if you look at this diagram, there are multiple layers inside a server. So there's a serving layer which takes requests from network and sends response back to the network. And the business layer in the middle, which includes many business logics about the service. And business layer connects to two layers. One is storage layer, which retrieves data from storages, and the other is client layer, which connects to external services and gets the data from it. Being asynchronous starts from the serving layer. So this is the entry point and also the most important point. So for us, the choice was easy since Line was developing the asynchronous client library named Armeria. So we used it as an early adapter. Then, next is the client layer on the right. Also needs to be asynchronous, but Armeria also supports HTTP or Thrift-based RPC client, so it was an easy choice for us too. But next is storage layer. Things get more complicated from here. So actually, not many storage clients supported asynchronous client. Like the storages like MySQL, HBase, Redis did not have asynchronous client, at least at that time we implemented OpenChat server. So also, business layer needs to gather the data from storages and also other external services and need to process all those asynchronously. So for the storage layer and the business layer, we needed a good library to support asynchronous processing. So for that, we adapted RxJava, which was the only valid option for us at that time. So here's the details. As I said previously, Armeria is used for serving layer and client layer in the RPC and Thrift client. And for Redis, we use Lattice on asynchronous client. So we recently migrated from a synchronous client named Jedis to Lattice recently. So for MySQL and HBase, we are using synchronous client like JDBC for MySQL and also the official HBase client for HBase. So in order to make them asynchronous, the specific thread pools are assigned. RxJava uses those thread pools and handle the request and make the asynchronous structure in these layers. So this is a sample code of send message API in the business layer. So here, like check chat or check related message, send message, those are all the objects RxJava creates. Like check chat or check related message, they call some calls to MySQL or HBase and validate whether the request is valid or not. And also, after checking everything, then it passes the data to send message object. Then over there, it actually tries to store the message and then try to send all the events from there. Then everything is worked well, then send message response is created, and that is returned to the Armeria. So let's see how it worked in reality. So in December 2017, there was an issue with some of our MySQL hosts. So MySQL version we were using had a thread-related bug on the specific queries, and 2 hosts were affected by that. And 2 hosts could not respond to the request anymore and got really slow. But the whole application servers were not affected by that much. Only the users who had data in those 2 hosts could not send or receive any messages. So we think that it was the achievement or our asynchronous structure we've made. If synchronous code was used, we must have had some outages at that time. So up until now, I explained 3 technical challenges and how we try to resolve them. Let's wrap up the technical discussion now. So in summary, OpenChat was born with the technical problems related to the scalability because of the increased member size. For that, we tried to solve this scalability problem by 3 perspectives: storage, delivery, and servers. So those have worked pretty well as we designed since the service's launch. But still, there are many things we have to do in the perspective of scalability. So you can see some of the future works here. So for the storage part, more automation is necessary since what we've done so far were manual processes. And also we are thinking about expand the usage of pre-sharding among line corporation. For delivery, we need to do more optimization about events because we are observing an active chat, and also we expect to have even more active chats in the future. For server part, many new libraries came up like Reactor or R2DBC and more. We also recently migrated to RxJava 1 to RxJava 2. So we'd like to keep up with the latest trend and latest libraries. And since many microservices are launched in line after we designed, so we are currently applying like circuit breakers or more technologies for stability. So this is the end of my presentation. I hope that you could see the inside of OpenChat from the perspective of scalability. Thank you for your attention. And please use OpenChat if you're interested and give us more feedbacks. Thank you.